In Module 3, Part 5, we're going to be introducing a new thermodynamic property called enthalpy, and we'll continue our discussion of the first law of thermodynamics for control mass. So, what is enthalpy? So, before we get started with what enthalpy is, let's try and derive how we can derive that value for enthalpy and what enthalpy actually means. So, enthalpy is denoted by the letter H. So just so everybody knows, enthalpy is H, and specific enthalpy is written as a lowercase h. Now, in order to derive this, we're going to take an example problem and sort of work out how we come with the term enthalpy and why it's useful to have enthalpy. Okay, so let's take an example where we have our usual piston cylinder device, and our piston cylinder device has a certain gas in it, and we have a position 1, and then that gas has some work, does some work, and eventually we get to a second point 2 that is higher up. And some of the things that we're going to write down the ideas that we're making and the assumptions that we're making throughout this problem. So the first assumption is that the problem is control mass, which means mass does not change. Okay, so it's a constant mass. We're also going to assume that this is a quasi-equilibrium problem. Okay, if we go back to our initial modules, we talked about quasi-equilibrium, what it means. And also that it's a constant pressure problem. So we have no resistance that changes throughout on the piston. The resistance is always the same, therefore the pressure is constant. Okay, we have no changes in kinetic energy and potential energy. And finally, the only work done is boundary work. So we're going to assume that the only work done is boundary work, and that boundary work is really what we were describing in the first 3 lectures of Module 3. So boundary work is the only work associated, and therefore we can apply this first law to this very simple problem. So what if we applied the first law? So remember, the first law is Q from 1 to 2 minus work from 1 to 2, or it can also be written as Q in minus work out. Okay, whichever way you prefer to write it, that's fine. And it's equal to U2 minus U1. Okay, those are capital U's, plus delta KE plus delta PE. And we conclude from our assumptions that we made in our initial prompt that kinetic energy and potential energy go to 0. And so we're left with the term that says Q from 1 to 2 minus work from 1 to 2 is equal to U2 minus U1. And we can go even further than this and say that Q from 1 to 2 is now equal to U2 minus U1 plus Q from 1 to 2. Okay, and we also know from this equation, this should be work from 1 to 2. We also know that from this equation, we know that work from 1 to 2 is equal to the boundary work. And this boundary work is the integral from 1 to 2 of PdV. Now, we can substitute this PdV in the above equation. So we have that Q from 1 to 2 is equal to U2 minus U1 plus the integral from 1 to 2 of P dV. And we also know that this is a constant pressure process. So we're told in the prompt that this is a constant pressure process. And we know it's a constant pressure process because we have no weights or no stops on our piston cylinder. Our piston cylinder is open and the piston is free to move. And since it's a constant pressure process, we can take the P out of this integral. The P is constant. And what that means is that we can rewrite the equation as Q from 1 to 2 is equal to U2 minus U1 plus P2 V2 minus P1 V1. And I'm going to write a little statement below this. So this is for this particular case. What it means is that the heat transfer is given in terms of deltas in the quality of U plus PV. So I'm going to write it down. So for this case, and for the specific case, the heat transfer is given by U plus PV. And this U plus PV is what we call enthalpy. Now, if we rearrange the equation above, we can also write Q from 1 to 2 is equal to U2 plus P2 V2 minus U1 plus P1 V1. And this is essentially what enthalpy is defined as. Enthalpy is defined as the internal energy plus the work term within that internal energy directly related to it. And we can write that H is equal to U plus PV. So it's essentially a term for us to have some shortcuts and to figure out faster what values could be in certain situations. And we'll look at certain situations where enthalpy is a lot easier to use than internal energy and then finding PV every single time. The specific enthalpy is equal to the following. So specific enthalpy, as we had defined, is lowercase h is equal to lowercase u plus p times lowercase v, or the specific volume. Okay, remember this is per unit mass. And what that means is that the units for this are usually kilojoules per kilogram, and the units for this are kilojoules. And the word enthalpy comes from, Greek enthalpion, which means to heat. So it's a combination of properties. It's a combination of U and PV. And it will appear in other examples than just constant pressure. So we're going to be using other examples than just constant pressure. Now, in many cases, and this is just a discussion, we don't really need to know this, but in many cases, internal energy is not listed in thermodynamic tables. So in our tables, they are listed, but in many cases, they are not. And enthalpy is used to back calculate U is equal to H minus PV. So we usually have enthalpy in our tables, and then we work back to find the internal energy. Luckily for us, we already have the internal energy in the table, so we don't really need, we can separate the two. Now, the reason why we use enthalpy instead of internal energy is that enthalpy is a lot easier to calculate and to find from experimental data. So actually what experimentalists do is they make tables for enthalpy, and then they calculate from the amount of pressure and volume that they use, they calculate U. And in the same way as specific volume and internal energy, the saturated mix equations hold true. So H is equal to 1 minus X times HF plus X times Hg. Or you can use the other form of the equation, which I don't prefer, which is HF plus X HFG, where HFG is the difference between Hg and HF. But I highly recommend using this first one. Okay, so we know how to use tables, and we've done some examples on how to use tables for internal energy, how to use tables for enthalpy in your study problems from Module 2. Now, the next question I have for everyone is, how do we find internal energy and enthalpy if we don't have tables for solids, liquids, and gases? So I'm going to write down the question. How do we find internal energy and enthalpy if we don't have tables? For solids, liquids, and gases. So if we have water or R134A, we can very easily use our tables to find U or H. We did this in the previous part. Now, in this case, we can't really do that. If we, let's say we have air and we don't have tables for air, we actually can't find internal energy, for example, for air, because we don't have those tables. Now, we do have some tables for air, and we'll go through them a little bit later in this module, but usually our shortcut when we do not have tables is to use specific heats. And what does specific heat mean? Specific heat is defined as the amount required of heat. So it's the amount of heat required per unit mass to raise the temperature of a substance by 1 degree. Okay, and it can be 1 degree Celsius or 1 degree Kelvin or 1 Kelvin. It's exactly the same thing. Okay, raising the temperature by 1 Kelvin or raising the temperature by 1 Celsius is the same thing. The only difference is where the zero lies. And we have two types of specific heats. We have a constant volume specific heat, which is CV for constant volume, and we have a constant pressure specific heat, which is CP. Now, to find delta H or delta U, we need to use CP or CV for water. So let's say we start with so just to give you an idea, to find delta H and delta U, we need to find the CV or the CP. So we use CV or CP. Now, the CV, if we take the CV, and right now it doesn't make sense, but it'll make sense in a second. If we take the CV of iron, for example, the CV of iron is equal to 4.5 kilojoules per kilogram Kelvin. Okay, and the CV of water, so I'll just put CV of water, is equal to 41.8 kilojoules per kilogram Kelvin. So what does that mean? That means that the CV of water is 9 times higher, around 9 times higher. What that means is you need a lot more energy to heat up 1 kilogram of water by 1 degree Kelvin than iron. You need very little energy to heat up iron by 1 degree, 1 kilogram of iron by 1 degree. So there's two cases, and there's two different cases that experimentalists did. So they explored two different cases, and then they recorded their information. One case is using constant volume, and one case is using constant pressure. And the values are different for the constant volume specific heat and the constant pressure specific heat, depending on the system that is being studied. So let's take helium. Let's take an example for helium. And let's say that on one side, we have helium with inside a box, and this box has a volume that is constant. Okay, the volume inside the box is constant. We have a mass of 1 kilogram of helium. Okay, so we have a mass of 1 kilogram of helium, and the change in temperature of that helium is 1 Kelvin, or 1 degree Celsius. And we have the same exact system in a piston cylinder form with the piston cylinder free to move up or down. And now we can say that the volume is not constant, but the pressure is constant, right? If we start heating it up by 1 degree, our piston is going to move. If we increase by 1 Kelvin on the left side in our constant volume box, the pressure is going to increase, but the volume is not going to increase. Okay, the volume is fixed. So we have the mass is equal to 1 kilogram as well. And we have that the delta temperature is equal to 1 Kelvin as well. Okay, or 1 degree Kelvin. Okay, and this is the experiment that they developed for constant volume. And this is the experiment that they developed for constant pressure. So at constant volume, they find the amount of energy it takes to heat up 1 degree, by 1 degree, 1 kilogram of helium. And on the right side, they do the same thing. They increase the temperature of helium by 1 degree Kelvin for 1 kilogram of mass, and they get the amount of energy used. So which one, pause the video here and think of which one will require more energy. Would they require the same energy, or would one require more energy than the other? Well, the answer is that CV on this side is equal to 3.12 kilojoules per kilogram Kelvin. So it takes 3.12 kilojoules to increase 1 kilogram of mass by 1 degree Celsius, or Kelvin. On the right side, the Cp is equal to 5.19 kilojoules per kilogram Kelvin. And what is the reason for this? The reason is because on the left side, so in the CV version, we are just supplying heat. So we supply heat, and the heat just works on heating the gas up. On the right side, the energy supplied does two things. The energy supplies to heat the gas and to move the piston up. So on the left side, our system is doing double. The heat that is supplied to that system, the energy supplied to that system, is not only heating up the system, but it's also helping move our piston up. Whereas on the left side, we only have heat converted to temperature. So essentially, on the left side, we have something like this. We have that the Q is equal to U. On the right side, we have Q is equal to H plus, U, so the internal energy, plus PV. And that's the difference. And if you remember, this is H essentially. Okay, so the amount differs by the fact that we had to move the piston as well. So I want that to be very clear. Okay, now how do we express Cp and Cv in terms of thermodynamic properties? How do we come up with an equation for Cp and Cv in terms of thermodynamic properties? Okay, so let's try and figure it out. So Cp, Cv in terms of thermodynamic properties. How do we do it? Well, let's look at the constant volume system. So let's look at the constant volume system first. Let's look at CV. So we already kind of alluded to it, but we have the constant volume system. So we have constant volume. Now this constant volume system, if we add some energy to the system, so let's say our heat goes up, then we know that our temperature is going to go up. And therefore, since we increase the temperature and energy, we increase the internal energy. So CV, from its definition, can be defined as du over dt, with a little v at the bottom to show that it's at constant volume. So essentially, CV is equal to the change in U, okay, and it's specific this time because we're looking at a per mass system per 1 kilogram, and with temperature, so it's a change in U with temperature at constant volume. Conversely, if we look at our system of our piston cylinder, we increase the temperature by 1 degree, which increases the internal energy, so it increases U, and it also increases PV. PV goes up, it changes. Okay, and we can write PV in with a little v or with a big V, it doesn't matter. It's the same thing. So it increases PV, and that means that the volume goes up. So in this case, we can say that what changes is U plus PV. Or if we write it in terms of the equation for CP, since it's per mass, it would be equal to du plus PV. So du plus PV divided by dt at constant pressure, and we can rewrite this as just dH over dt at constant pressure, which is equal to the change, or is in words would be equal to the change in H with T at constant pressure. So these expressions are independent of the type of process and the process itself. So these equations can be used for any type of process. And in the end, what we're just trying to use is we're trying to say, how do we now apply this definition of CV and CP? Well, we have these two equations, so let's try and use them for solids and liquids. Let's look at solids and liquids and what happens. So if we apply these to solids and liquids, we can say we know that H is equal to U plus PV, lowercase u. And if we differentiate this value, we get dH is equal to du plus PV plus, PdV plus V dP. And we can simplify this equation a little bit by looking at this term specifically. What can we say about solids and liquids? We usually say that solids and liquids are usually, so S plus L, okay, solid plus liquids are usually incompressible. And what incompressible means is that dV is usually very close to zero. Okay, it's approximately zero, so not exactly zero, but it's very, very small. And what that means is that we can sort of get rid of this term for solids and liquids. So how does that help us? Well, we can say that dH for solids and liquids, we can say that dH is equal to du plus V dP. And if we integrate this term we get delta H is equal to delta U, lowercase u, plus V delta P. Now, for solids and liquids, V is usually very small. So remember, V is equal to meters cubed per kilogram. Okay, so it's the opposite of density. and V is usually very small for liquids and solids. So what we can do is we can say, for the interest of the equation and the interest of solids and liquids, we can actually solve our problem and say, let's make this close enough to 0 that we can get rid of it. And what that means is that we can say that dH is actually equal to du for solids and liquids. Okay, now what if we divided both sides by dt? So now we can divide both sides by dt. So dH over dt is equal to du over dt, which is equal to a constant. And this constant is actually the definition of Cp is equal to Cv for liquids and solids. So we've just proved that for liquids and solids, by assuming that we have incompressible and the fact that our specific volume is very small, so we have a lot of kilograms per meters cubed, we therefore can say that Cp is equal to Cv for solids and liquids. And if we take the equation of Cp is equal to Cv, we're going to say that this is equal to just C. So for solids and liquids, we're just going to call it C. It's not going to be Cp or Cv, it's just going to be C. Okay? C is just going to be our specific heat. Okay, so it's just going to be called C without a sub change. And if we look at this equation up here, or let's go to, so if we look at the equation up here for either dH dt or Cp is equal to du dt, we can now write out this equation and rearrange it. So we can say that for solids and liquids, we can say that du over dt is equal to dH over dt, which is equal to C. Okay, that's our new term. And we can now rearrange the equation. We can say, we can bring the temperature to the other side. So we can say that du is equal to dH, which is equal to C dt. And if we integrate this equation, we can find out, so if we integrate all three terms, we find out from 1 to 2, we find out that U2 minus U1 is equal to H2 minus H1 is equal to C times T2 minus T1. Or delta U is equal to delta H is equal to C times delta T. So if we don't have tables for liquids and solids, it makes it very easy to solve a problem with the first law. Let's say we have our first law that says Q in minus workout is equal to delta U plus delta KE plus delta PE. We can now, let's assume that KE and P goes to 0. Okay, just like before, we can assume that in some cases. We would be left with delta U. And delta U is mass times U2 minus U1. Well, now, if we don't have tables, let's say it's another liquid, it's oil, for example. Instead of having water, we have oil. Or even if it's water and we don't want to use the tables, we can now say we have a substitute for this U2 minus U1. The substitute is C for oil, if it was oil, times temperature 2 of the oil minus temperature 1 of the oil. okay? And the best way to study this is to do an example. And your values for C are found, so values for C are found in tables A2 and A3. So appendix A2 and A3. So the first example we're going to be doing in this case with this application of this new theory of specific heat to an example problem is to look at two different pieces of two different materials mixed together and seeing what happens. So we are told that we have a 50 kilogram iron block. So I'll write example here so we know it's an example. A 50 kilogram iron block at 80 degrees is dropped into an insulated tank and this insulated tank contains 0.5 meters cubed of liquid water at 25 degrees Celsius. And we're told to determine T, so the temperature when thermal equilibrium is reached. So we have to find temperature essentially at time 2. Okay, so we're going to have, let's draw a little bit of our system. So we have a tank like this, and we'll say that it's perfectly insulated. So we'll put like walls around it, say that it's insulated. And initially we have water at 25 degrees Celsius, and we put in it a piece of iron, and the iron is at 80 degrees Celsius. Okay, so that's the information we're told. Now, some of the assumptions we're going to make, and those are assumptions that you can make as well, but the assumptions that you would make in this type of system is that the change in kinetic energy is equal to 0, and the change in potential energy is equal to 0. We're assuming this because we're assuming that we have a stationary system. Okay, a system is not moving, therefore we have no change in kinetic energy. Okay, and we also know that the system is insulated. And if we know that the system is insulated, we know that if we define a boundary of our system to be this boundary here, so we look at our whole system and we put a boundary around our system, we can say that the boundary means that no heat, and I'll leave it in red on purpose, no heat is coming into system. And what that means is that if we do an equation based on the whole system with the iron and the water, we can say that Qin is equal to 0. Okay, so the next step we're going to do in this type of example is to do a first law analysis to try and find the temperature. So we're going to do a first law analysis. And that means writing down the first law essentially. Okay, and then figuring out what happens. So we have Qin minus work out is equal to change in internal energy plus change in kinetic energy plus change in potential energy. And we already know that we're assuming that the change in kinetic and potential energy is equal to 0. And we also know that Qin is equal to 0. We can delete that. The other thing we know is that, is there any work in the system being done? No, there's no work in the system. We're in an insulated tank. The volume cannot change. Okay? The volume can't change in a tank, only in a piston cylinder device. Okay, so the volume is not going to change, and if the volume doesn't change, it means that we have no work. Nothing is moving. Okay, we can also assume this because we can assume that it's incompressible. So the liquid and the solid are incompressible. Therefore, we can say that work is equal to 0 as well. And so we're left in our equation with just our delta U alone. And so we're left with delta U is equal to 0. Okay, and delta U is delta U of the system. The system is defined by the boundary that we made. This is the system. The system is inside of here. Okay, so we can say the delta U of the system is equal to 0. There's no change in internal energy in the system throughout. Now, there is a change if we know that we're putting something with 80 degrees of temperature into water at 25 degrees, we know there's going to be a heat exchange between the two. The temperature is usually going to reach some sort of equilibrium. Maybe it's 30 degrees, maybe it's 50 degrees between the iron and the water. We're going to heat up the water and we're going to cool down the iron in the process. So we can separate the delta U of the system into the two parts inside our system. So we can separate them by delta U iron plus delta U water. Okay, we have two different systems, so we're going to separate them in two. And we can now write this equation. We can say that it's still equal to 0, and we can rewrite it in terms of mass and specific internal energy. So we would have mass of iron multiplied by U2 minus U1 plus the mass of water multiplied by U2 minus U1 for water. So this is for iron. I'll put an I and W for water. Okay, so I is iron, W is water. And now what we can do before we get started with finding values for U or trying to solve for the problem, we can say, let's look at state 1 and state 2. Let's look at the two different states that we have. So state 1, we're told that for iron, the mass of the iron, so Mi, is equal to 50 kilograms. And we're told that T1I is equal to 80 degrees Celsius. Okay, and we're told at state 2 to essentially find the final temperature of the iron. So we're trying to find T2. For the water, we have V1 is equal to 0.5 meters cubed. And we have T1 is equal to 25 degrees Celsius. And we also have that at state, so this is state 1. And then at our final state, we're looking for our temperature 2. And we also know that volume 2 is equal to volume 1. Okay, the volume does not change. Now, are we given pressure for the water? We're not given any pressure for the water. Since we're not given any pressure, we can't really use our tables to find values for U2 and U1. We're only given temperature. That's it. We're not even given mass. So we can't find from temperature and specific volume, we can't find U2 and U1. And actually, that's going to be a little bit easier for us because we're actually trying to find T2. So we can find T2 in a different way. So in this case, because we don't have pressure, because we only have one value for water, we will use C instead of tables. So we're going to use the definition with C instead of tables. And the reason we do this, and we usually do this in problems where we have a mix of something else that doesn't have tables, we do this to sort of solve for our equation. So if you remember correctly, for solids and liquids, we have the definition that U2 minus U1 is equal to C times T2 minus T1. Okay, so we have this definition. And we can now plug in this definition into our equation above. So we can say that delta U is equal to 0, which is equal to mass of iron, Mi, times C T2 minus T1 of iron. Okay, so T1 of, I'll just put I, plus the mass of the water multiplied by C times T2 minus T1 of water. And if you look correctly, the temperature 2 of iron and the temperature 2 of water are equal. So we can make them just equal to each other and they're both the same temperature. So we can say that T2 water is equal to T2 iron. It's the final equilibrium temperature. We know that that's the final temperature. So now, what are the terms that we have to find? So we know that we have to find T2. That's our final term. Okay, I'll put it in green. So we have to find T2. We now have to find, we have the mass of iron. So we have to find C for iron. We have to find C for water. So these C's are specific to iron and water. And we also have to find the mass of water. We also have to find the mass of water. We're given the volume of water, but we don't have the mass of water. And we have the temperature initial. So the first thing we're going to do is find the mass of water. So how do we find the mass of the water? Well, the mass of the water is equal to V over specific volume. So what we can do is we can go to table A4 and assume that we have a saturated liquid, okay, because it's pretty much incompressible. We can use our compressed liquid rule, where we say we have a compressed liquid. We know that. Therefore, V is equal to Vf at temperature given. And that temperature given is 25 degrees. So we have a given temperature in the question of 25 degrees Celsius. So we can go and find, so we know that the volume of the water is 0.5 meters cubed, and we're going to go find our V in table A4. So we go to table A4. We go to table A4, and we can go to 25 degrees Celsius and find our VF. And our VF is 0.001003. So we can plug that back in. So we can say that this is from tables 0.001003. And we can say that that's equal to 498.5 kilograms. So it's equal to 498.5 kilograms. Okay, that's the preferred technique for the problem. Now, in your textbook, this is also example 4.12 or 4-12. In your textbook, what they do instead of using specific volume is they say the mass of the water is density times the volume, which is the same thing. And they go to their tables and they go to table A2 and they use the density of water. They use the density of water, which is here, of 997. And by using the density of 997, they get a value very similar. But they actually approximate the value to be equal to around 500 kilograms. So they don't use as many decimal points, and so they get the value as 500 kilograms. I think this technique is better. So I think we're going to stick with this technique, but just know that the example does it a little bit differently in the book itself. Now that we're going to be using 500 moving forward so that we equal the example. So the mass is actually, we're going to use 500 as a mass. The next thing we have to find is the two C's. So we need to find C for iron and C for water. So C for iron is equal to the following. So let's go to table A2. In table A2, we see that we have ideal gases and more ideal gases. So we're going to go to table A3, where we have properties of common liquids, solids, and foods. We then go to our solids, which are in part B, and we try and find our C for iron, which is right here. And if you look, we have a value of, so the book uses CP. So whenever you have a solid or liquid, the book will always use CP, but we remember that CP is equal to CV for a solid or liquid. And in our case, we're going to call that just C. Okay, so C is going to be equal to 0.45 kilojoules per kilograms Kelvin. And for water, we also have to look for a value. So for C of water, we now can go look through, go back to this part, and we have our CP, which is on the right here. So we have CP of 4.22, 4.18, 4.18, 4.19, etc., etc. Now, what CP are we going to use? Are we going to use 25? Are we going to use 50? Are we going to use 75? Well, our starting temperature, our initial temperature is 25 degrees. So we start with T1 is equal to 25 degrees. T2 might be equal to 50 degrees. Okay, our final temperature might be equal to 50 degrees. So we have to choose a C of water that's called C average. So we have to find the average specific heat for two different temperatures, for example. Okay, so if, for example, if you knew the final temperature and water was, for example, started at 50 degrees, started at 25 degrees, and ended at 75 degrees, you would have to use C average at 50 degrees Celsius. Now, in our case, it starts at 25 and could go all the way up to 80 degrees, right? It could go all the way up to the temperature of the iron, or very close to the temperature of the iron. So we have to make some sort of assumption and then double check our assumption. So we're going to make an assumption that we're going to start with C average at 25 degrees Celsius. And I'll delete this for now, just so it doesn't confuse us. But we're going to assume C average is 25 degrees. And if you look at the value for 25 and 50, you actually get the same value. So there's not that big of a difference. So C average is for seawater at 25 degrees is equal to 4.18. Now, going back to iron, we also use the average temperature for iron. But if we look at iron, we only are given one temperature. If we had, on the other hand, for example, aluminum, and we had a temperature of aluminum that started with 400 Kelvin and then went down to 300 Kelvin, we would have to use the value that's average. Okay, and you'll do some examples in your study problems, and we'll do some examples in class as well, where we might have this sort of value that we are looking for to be as close as possible. Now, in this case, I do not want you to interpolate. Okay, I do not want you to interpolate. You just find the closest value to your temperature. So let's continue the problem. So we've assumed that the C average was 25 degrees, and we're going to check later if that's okay or not. For C iron, we only have one value, so that's fine. And just to clarify this, it means that U2 minus U1 is equal to C times T2 minus T1 is actually equal to C average. And this means the temperature average, okay, between T2 and T1. In this case, we don't know T2 yet. So we don't know the average, so we have to guess. Okay, so C average is the average temp between T1 and T2. Okay, and so now that we have our values for C, we can write our equation out. So we have 50 kilograms of iron multiplied by 0.45 multiplied by temperature 2 minus 80 plus 273. Okay, you don't necessarily have to convert to Kelvin here, but I always like to convert to temperature in Kelvin just to make sure I'm not making a mistake. Since it is a change in temperature, you don't have to use Kelvin, but I prefer using it just to make sure that we are fine with our units. Plus 500, which is our estimated weight of the water. Okay, we're assuming a little bit of a wrong value, but that's what the book does, so I'm following what the book does, even though the real value would be 498.5. And we multiply this by 4.18 and T2 minus 25 plus 273 to convert to Kelvin, which is equal to 0. And throughout this math, we can say that T2 is equal to 298 Kelvin, which is equal to 25.6 degrees Celsius. So our final temperature of our iron and water is 25.6 degrees Celsius. Okay, so very close to the initial temperature of water. So now we can go back and see if our assumption was correct. So we assumed that C average was 25 degrees. And we were correct in that assumption. T1 is 25, T2 is 25.6, so we're very close to 25. It's our closest value. So we can say this is okay. Now, if you had a final temperature of water of 75 degrees, then you would have to use C of water at 50 degrees, which in this case is actually the same as 25, but you need to write C average at 50 degrees. If you wrote C average at 25 degrees and it turned out that the average temperature was 50 for some reason, then you would get it wrong. If the average temperature was, let's say, if the average temperature was 35, so if you had 25 and another temperature, and the average was 35, you would still use 25 as your value. So you would still use because it's the closest value. I don't need you to interpolate between the values, just like in your tables, so you do not have to interpolate. Okay, so this concludes part 5 of our module 3, and we'll be back in part 6 to discuss gases and how we can apply these equations to gases.